Greetings and welcome. In this chapter, we'll be reviewing quite a number of topics that you've probably had in the past, but I encourage you not to skip this chapter because we're really laying a nice foundation for all of our future discussions. We're going to start here with the set of numbers that we're primarily interested in, and that set is the set of real numbers. Now, real numbers have a number of subsets involved within that set, and we want to talk about those subsets just a little bit. Real numbers are composed of rational numbers and irrational numbers. When the word rational is used, it should bring to mind the idea of fraction, because rational numbers are defined as all the numbers in the world that can be written in the form a over b, where a and b are integers and b is not equal to 0. Denominators of fractions are not allowed to be 0 because it causes the fraction to be undefined. Now, the kinds of numbers that would be in this set of rational numbers would be all of these numbers. 4 can be written in the form of 4 over 1. So if it can be written in this form, it's a rational number. Common fractions are in this set. Also, decimals that are terminating, like this one, would be in this form, because 5 2/10 could be written as 5 and 2 over 10, or 5 1/5, which can be written in an improper fraction form, just like that. Repeating decimals also fall into this category. 0.25, 25, 25, and so on forevermore turns out to be 25 over 99 in this form, the form of a rational number, so that's a rational value. So in terms of decimal numbers, all decimals that are either terminating or repeating fall into this set. Now, you might be wondering, gee, what does that leave for irrational numbers? Well, I'll get to that in a minute, because rational numbers actually have a number of subsets involved within that set. And I mentioned the idea of integers a few moments ago, but if we start with the most basic subset of rational numbers, it would be the set of natural numbers. Natural numbers are composed of the numbers 1, 2, 3, 4, and so on. If we put 0 into that set, just kind of add 0 to the natural numbers, we have the set of whole numbers. If we take the set of whole numbers and then the negatives of all of the natural numbers and put that all together, we have the set of integers. And then the integers, along with common fractions, bring us to the idea of rational numbers. Well, what numbers are we talking about with irrational numbers? Well, those would be decimals that never end and never repeat. So never ending and never repeating decimals would be the set of irrational numbers. And numbers that fall into that category would be like the square root of 5 or the square root of any non-square, pi, the naturally occurring constant pi, e, which is also another naturally occurring constant, and we'll have a lot to say about that later. But at any rate, these two sets together give us the set of real numbers. Now, real numbers are often pictured by using a real number line or simply a number line. This is a number line. Now, we're including not only the integers that are written under here, but all of the items that are in between these integers as well are contained on this number line. Now, 0 is called the origin of the number line. Positive numbers lie to the right, negative numbers lie to the left. There is a one-to-one correspondence between points on this number line and real numbers. That is, for every real number, there's a point on the number line that is its graph. And for every point on the number line, there is a real number that is its coordinate. So one-to-one correspondence. For every one number, there is 1 point, and for every 1 point, there is 1 number. The number line allows us to establish an order relationship between any two real numbers. And given any two special numbers, it's pretty easy for us to establish that relationship. -2 and 3, for example. Let's see, what's the order relationship? Well, numbers that lie to the right are greater than numbers that lie to the left. Numbers that lie to the left are less than numbers that lie to the right. Now, you may recall that there are a couple of little symbols for greater than and less than. And if we're talking about -2 and 3, we say that -2 is less than 3. Now, this symbol then means is less than. If you ever forget the way the symbol goes, whether the little arrow points to the left or the right to mean less than or greater than, you ever forget that, just remember that the little arrow points toward the smaller number in all cases. So if you forget, all you have to do is write a couple of numbers that you know the relative size of, make the arrow point toward the smaller one, and read it as you understand it. 5 we understand is greater than 1. Oh, this symbol means is greater than, so greater than for this symbol. Okay, so that's the idea. Now, the inequality idea is, as I mentioned, the symbols are these: less than, greater than, less than or equal to, greater than or equal to. Now, it's often the case that letters are used in this inequality situation, and there are several ways to describe an inequality when letters are used. One way is to use an inequality statement, and this one says x is less than 2. Another way to describe this inequality is by using a graph. Now, to use a graph, you just write a number line and then identify the important point or points on the number line. Here we're describing real numbers that are less than 2. So we identify the position of 2 on the number line, and then we shade the real numbers that are less than 2. That would be the real numbers that are to the left of 2 on the number line. Notice that a parenthesis notation is used here to indicate that 2 is not included in the group of numbers that we're describing here. If we wanted to include the 2, we would put a bracket indicator here, and we would have as an inequality less than or equal to, you see. Another notation that's useful here to describe the same set of numbers is called interval notation. And we're describing an interval on the number line from negative infinity to 2, but not including the 2. So we simply write negative infinity comma 2 to establish the interval. And now we want to describe whether or not the endpoints are included in this group of numbers that we're describing. Now, 2 is not included in this group of numbers, so we use the parenthesis indicator. We say that this end of the interval is open because there is no last item. You see, the 2 is not included here. And since there is no last item for infinity, we use the open indicator on that end as well. Now, since both ends of the interval notation are said to be open, this is called an open interval. All right. Let's go through another one. For this one, x is greater than or equal to 4, and we would then draw a real number line and identify the position of 4. Notice I'm using only a single arrowhead here. You may have noticed this notation earlier when the animation came up, and you may have wondered why in the world was only one arrowhead used. After all, we have numbers in both directions. Sometimes teachers use this kind of notation to emphasize the direction of greater numbers. You see, the greater numbers lie to the right, the smaller numbers lie to the left, and that kind of thing. Positive over here, negative over here. We kind of know about that routine anyway, but this is sometimes used for emphasis in that regard. Now, also, sometimes teachers like for you to emphasize the position of 4 relative to some other numbers, just to verify that you know where the greater or lesser numbers lie. So we would also introduce a 5 and a 3 here on the number line for that purpose, if that's what's needed. Well, at any rate, we're describing real numbers that are greater than or equal to 4. 4 is included in this group of numbers. So we use the bracket indicator rather than the parenthesis, and we shade to the right of the 4. And we'll also shade the arrowhead. And I might put the arrowhead on the other side as well. For the interval notation, we want the interval from 4 to infinity. So we write 4, comma, infinity. We want to include the 4, but we're not including, or we're not showing a closed situation on the right side because of the infinity notation. Now notice the open indicator and the closed indicator on the other side. So this interval is said to be half open. Half open. For this one, we really have two inequalities in one. We read this as negative 2 is less than or equal to x, and x is less than 5. So we read this inequality, and then we read this inequality. So two inequalities in one. We can really think of this as a situation where the real numbers that we're describing are between negative 2 and 5. So using that idea, it's pretty easy to graph. You know, with a real number line, we identify the position of negative 2, the position of 5. We want the numbers that are between those two. And then the real trick is to decide whether or not those endpoints are included in the interval that we're describing. This says negative 2 is less than or equal to x, and so the negative 2 is included in our set of numbers that we're describing, but this says x is strictly less than 5, so 5 is not included. We use the parenthesis indicator on this end. For interval notation, it kind of follows what we have right here. It's the interval from -2 to 5. We want to include the -2, but we don't want to include the 5. And once again, since we have the open indicator on one end and the closed indicator on the other end, we have a half open interval. Now for 3 and infinity, let me slide back over here. For this, let's just fill in the other blanks. We have, notice an open indicator on both ends of our interval, and therefore we have an open interval. All right, back over here for the graph. Now, we want to describe the numbers that are in the interval from 3 to infinity. So with a real number line, we identify the position of 3, and 3 to infinity means to the right of 3. And we want to emphasize that we're not including 3 in this group of numbers that we're describing. So we use a parenthesis indicator at 3. And the inequality statement for this would be that our real numbers that we're describing, we'll use the letter x to be consistent here. The values are, these real numbers are strictly greater than 3. Here we have a graph with endpoints that are included in the interval. And let's describe this using the inequality statement. This would say that x is in between, their real numbers are between -7 and -1. We would say then that -7 is less than or equal to x, and x is less than or equal to -1. For the interval notation, it's the interval from -7 to -1, and we're including those endpoints. And since we're closed on both ends of the interval, this is called a closed interval. Absolute value can be thought of as distance from 0 on the number line. If we want to find the absolute value of 5 or the absolute value of -5, and notice the notation requesting absolute value, but in either of these cases we're just asking ourselves, what's the distance from 0 to these points on the number line? The distance is 5 for both of them. So we're noticing that absolute value will give us a number that is always positive or perhaps 0 in some circumstances. And that's kind of consistent with our idea of distance in the first place. If we're in Orlando, Florida, for example, and we're thinking about the distance to Miami or the distance to Atlanta, those two cities are in opposite directions from Orlando, and yet we use a positive value to represent both of them. You see, so it's the notion of distance, and it's very consistent with that idea. Now, there are some contexts where distance is directed. That is, it has a direction associated with it, and there's a positiveness or negativeness associated with it. And that might be a circumstance like, thinking about altitude. The altitude of an airplane and the altitude of a submarine. Well, the altitude of the submarine might be regarded as negative, you see. That's the idea. But here, we're talking always positive. Now, the only tricky circumstances involving absolute value have to do with when letters are involved. For example, if I'm thinking about this letter, x, and x stands for any real number, can you tell me whether that's positive or negative? Certainly not. We don't know. It could stand for any real number, and some are positive, some are negative. Now, what about this real number? Is that real number positive or negative? Well, we don't know. You see, the tendency is to think that because this little symbol is involved here, this minus sign, or this negative indicator, it implies that this is a negative number. Well, it's not. This just means the opposite of whatever x is. If x is positive, then the opposite of that positive number is negative. But if x itself were negative, then the opposite of a negative number would be positive. So this could indicate a positive number. Now, that idea allows us to write a general definition for absolute value. The absolute value of any real number a is equal to, and now we split the definition into two parts. One where the number itself is positive, and the other where the number is negative. And we include the 0 in this possibility as well, the positive one. So the absolute value of a real number which is positive would be the real number itself. You see, so the absolute value of a is equal to a if a is greater than or equal to 0, positive or 0, you see. On the other hand, the absolute value of this real number is the opposite of that real number if that real number is negative, if that real number is less than 0. All right, so that's the idea. The only tricky situations in dealing with absolute values where we are dealing with variables. Consider this problem. We have the absolute value of x over x. Now, consider the case where x is greater than 0. If x is positive, here's what happens. The absolute value of a positive number is itself. So the absolute value of x would be x. In the denominator, we have simply x. So we have x over x, or 1. On the other hand, if x is less than 0, if x is negative, you see, the absolute value of x then would be represented as the opposite of x. You see, this is a positive number when x is negative. All right, then in the denominator we have simply x. Reducing here we get negative 1. The idea of absolute value being associated with distance allows us to evaluate the distance between two numbers on the number line. Here we have a number line. Suppose we want to find the distance between 1 and 3. Well, it's pretty easy for 1 and 3. We can just count the units. From 1 to 3 we have, let's see, 1, 2 units, you see, real easy. But another way to do it is to actually do the subtraction or do an operation here. And one way to deal with it is to say it's 3 minus 1. Just take the larger number, subtract the small one, and we have that distance. And we don't always want to have to identify the larger of the two numbers, though, because a lot of times we don't even know the larger of the two numbers if the numbers aren't identified specifically. So we can introduce the idea of absolute value to deal with that. And in doing that, we could say that it's the absolute value of 3 minus 1, which is the same as the absolute value of 1 minus 3, you see. And in either case, we get 2 as the result. This allows us then to very generally find the distance between negative 2 and 3. It's the absolute value of the relative difference between those two. So it's take one of them, subtract the other one, and evaluate the absolute value. This is negative 5. The absolute value of negative 5 is 5. And most generally, the distance between A and B is the absolute value of the difference between them. One of the most important building blocks in mathematics is the idea of expression. An expression is a combination of letters which are called variables because the value for a letter changes from problem to problem, hence the idea of variable. All right, so expressions are composed of letters, numbers, and operations. And the operations are adding, subtracting, multiplying, dividing, exponentiation, absolute value, and there are others that we'll introduce later. But the combination of these gives us expressions, and here are a couple of examples of expressions. The prevailing characteristic here, by omission, is the idea that we have no equal sign. We have no equation involved here. Equations are composed of expressions. So here's a building block then for equations. But expressions then have this characteristic, this idea that they're composed of these items. And let's talk a little terminology here. Here we have an expression. The terms involved in the expression are the items that can be separated with plus signs. Now here we have a minus sign between these two items, but we could rewrite this as 3x squared plus negative 2x. And because we can write this separating with plus signs, then this is a term, that's a term, this is a term. Knowing this trick, we can very quickly identify the terms from the beginning. 3x squared is a term, minus 2x is a term, 5 is a term. Now, the terms fall into a couple of categories. We have variable terms and a constant term here. The variable terms are the terms that involve variables or letters, and the constant term is the 5 here. Coefficient refers to the number part of a variable term. Here, the numerical part, the numerical factor is 3. So 3 is the coefficient in this term. In this term, the coefficient is negative 2. Now, if we have a letter that's kind of a standalone, like, let's say negative n, the coefficient would be negative understood 1. So the coefficient negative 1 for that term. There are fundamentally two things that we do with expressions. One thing is to simplify them, to manipulate them in some particular way. And another thing is to evaluate them. When we evaluate expressions, we are finding the value of the expression when we are presumably given the value of some letter or letters that appear in the expression. Here, for example, if we want to evaluate this expression, we're given here the value that x is negative 2. So we want to find the value of this expression when x is negative 2. And in that situation, you simply replace x with the value given, and that becomes the first step in the evaluation process. So you make no calculations, you just do a blind replacement. You replace x with the value we have here in all places where we have an x. All right, and then we go through the evaluation process by performing indicated operations. Now, you may recall from a previous course that we have an order of operations agreement, that we agree that we perform operations within parentheses first. And we can even think of parentheses as meaning do this first, work within the parentheses first. And then we exponentiate after that. And then we perform multiplications and divisions from left to right. And then we perform additions and subtractions from left to right. Here, that comes into play right here with the parenthesis. We would look inside this parenthesis to see if there's anything to do. No, it's in simple form. So the next thing to do is to exponentiate. That is, we square the negative 2 before we multiply times 3. You see, the negative 2 is the base of the exponent, and if we multiply 3 times the negative 2 and then square, we are actually squaring the 3 as well as the negative 2. So we do the squaring first, and then 3 times 4 would give 12. The negative 2 times negative 2 is 4, and collecting, we find that the evaluation, or the value of the expression when x is negative 2, is 21. We're laying the groundwork now for a mathematical system called an algebra. And an algebra is actually composed of 3 basic elements. One is a set of numbers, which we already talked about. Another is operations that can be performed on those numbers. And then there are properties, which we're going to talk about right now. So those 3 elements compose the algebra that we're talking about. I want you to understand, though, that there are many different algebras. If we talk about a different set of numbers rather than the real numbers, we limit our set of numbers in some way, or redefine our set of numbers, or redefine the kinds of operations. We can define our own operations separate and apart from adding, subtracting, multiplying, and dividing. And we can create some properties that go along with that new number system and those new operations, and we can have a different algebra. You see, this is just the traditional, general algebraic system that we are so familiar with up to this point. Well, let's talk about some properties that we're probably already familiar with as well. We'll give them a rather formal names at this point, and we generally won't refer to these names in the future, but it's important to know that they are there. Commutative property. Now, there are 2 commutative properties. There's a commutative property of addition and a commutative property of multiplication. Commutative property refers to the order in which this operation, the operation implied here, can be performed. The commutative property of addition is illustrated by 5 plus 3 is equal to 3 plus 5. Or more generally, I could say A plus B is equal to B plus A. We can add numbers in either order. That's the idea. Same notion with multiplication. Commutative property of multiplication means that 5 times 3 has the same value, is the same thing as 3 times 5. Now, notice the order is the idea with the commutative property. Now, the associative property, on the other hand, has to do with the association of the numbers that are involved under a certain operation. The associative property of addition is illustrated this way. If we're adding 2, 3, and 4, we can add any 2 of them that we want to begin with. That's basically the idea. Now, I do want you to notice that we see this already, and we see that 3 and 4 can be added before we add the 2, or we can add 2 and 3 first and then add the 4, and it doesn't make any difference. So we are just changing the association of the numbers under this property. Now, notice that the order of the numbers hasn't changed. We have 2, 3, and 4 in that order, 2, 3, and 4 in that order. It's only the association of them, the grouping of them is the only thing that's changed. Under multiplication, it's the same idea. If I have 3 numbers to multiply, I can multiply those 2 first and then that product times 2, or I can multiply 2 times 3 and then that product times 4 and have the same result. Now, commutative and associative properties are generally not called by name, but the next one is called by name. We use it so often, I guess, or or it has a certain speciality to it that we do call it by name very often. It's called the distributive property, and it's illustrated like this. 4 times x plus 3 is equal to 4 times x plus 4 times 3. 4 times x plus 4 times 3. Of course, we would write 4x plus 12. So it's the idea that this 4 is distributing itself as a multiplier throughout the items in parenthesis. If we had 5 items in the parenthesis, the 4 would distribute itself as a multiplier throughout all of the items within parenthesis. This idea of distribution can occur from either direction. That is, if the 4 were placed over here, the 4 would still be multiplied times each of the items within parenthesis. Now, this notion of the distributive property works in both directions, and working in this direction, it allows us to multiply certain items like this, a monomial times a binomial, which we'll get into a little bit more later, but it also allows us to factor. If we're thinking about it in the other direction, if we start with this and think about that, we can take the 4 out of those two terms, you see, using the distributive property and go to a factored form. So the distributive property has a lot of different uses. These next properties are often referred to as existence properties. There is an identity, a couple of identity properties. There's an additive identity property and a multiplicative identity property, and really we're just saying that there exists an additive identity element and a multiplicative identity element within the algebra that we're talking about. Now, the whole idea with identities is maintaining the identity of some real number under an operation. You see, and here's how it works. We start with a real number like 5. We perform this operation of addition using this additive identity element, and we maintain the identity of the element that we started with. In a similar way, the multiplicative identity works like this. The multiplicative identity element is 1 because we can take a real number, we can perform this operation of multiplication using this multiplicative identity element, and we maintain the identity of the real number that we started with. So identities, the multiplicative and additive identity elements, exist within our algebra. Rather formal idea, but a rather intriguing one as well. Inverses. Now, inverse elements or inverse properties is what we're referring to here. There's an additive inverse element and a multiplicative inverse element in existence in the algebra that we're talking about. Now, an additive inverse is nothing more than an opposite, and a multiplicative inverse is nothing more than a reciprocal. Now, with additive inverses, if we take a number and under this operation of addition, you see we add its additive inverse, its opposite. When we take a number and add its opposite, we get 0. Now, notice that 0 is the additive identity element. And in that way, the inverses and the identities are related. In a similar way, similar idea, that we have a multiplicative inverse element involved with all of our real numbers, and it's nothing more than the reciprocal. We take a real number and we multiply times its reciprocal, and we always get 1. And 1 turns out to be the multiplicative identity element. So again, that relationship between inverses and identities. Well, there are a number of other properties that are listed in your textbook, and I invite you to have a look at them. There is a listing of properties of negation, properties of equality, properties of zero, properties of fractions. And the notion with equality, as you'll notice, is the notion that allows us to solve equations or manipulate equations. We can add the same number on both sides of an equation and maintain equality. We can subtract the same number and maintain equality. We can multiply on both sides and maintain equality, and so on. Ideas about zero. Zero, multiplying times 0 gives 0, of course. And 0 involved in fractions is a very important idea. And I'd like to show you some of the ideas within fractions. One of the things is that if we have 0 over 5, that's equal to 0. This is 0 divided by 5. It's the way to evaluate this. We could actually go through the long division process to show that our answer here is 0. In a similar way, we can show that 5 divided by 0 is undefined. Let me show you that right quick. This is so important. We disallow the idea that 0 can appear in a denominator because it causes the fraction to be undefined. And it's undefined because of this. A fraction implies a division problem. And if we just turn this into a little division problem, kind of like this. If we say this is 5 divided by 0, then it's 0 into 5. And this is a request for some number, which when multiplied times 0 gives 5. Is there any number that multiplies times 0 to give 5? No. Therefore, this is undefined. You see, there is no real number that can be multiplied times 0 to give 5. So that's why this has to be undefined. That's undefined. Also with fractions is the notion of a sign, a minus sign. Now, if we have negative 2 over 3. There are really 3 signs in this fraction. There's the sign of the numerator, the sign of the denominator, and the sign of the fraction itself. And this minus sign can float to any of the 3 positions. In fact, you can think of it like this, that in these 3 signs you can change any 2 of them. So if I change this sign to plus and the sign of the fraction to minus, I get minus 2/3. But that's the same thing also as 2 over negative 3. See, all these say the same thing. So when you have a sign, a negative sign in a fraction, it can float to any of the 3 different positions.